No, I thought I said
Too late. It started.
It.
All right, exercise 14 is where we're going to pick up where we left off from yesterday. So, remember, percent dissociation, which we talked about yesterday, is the amount that dissociates divided by the initial amount that you have times 100. Okay. So, lactic acid is a waste product that accumulates in muscle tissue during exertion, leading to pain and a feeling of fatigue. In a 0.100 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value of Ka for this acid. Okay? So I want to know the value of Ka. All right? So can I look at this right now and write an expression for Ka? Yes. All right. So let's figure out what I need to know for Ka. So Ka is going to be equal to what? Products over reactants. So before I can do products over reactants, I need to write out what this equation is going to look like, right?
Yeah.
So I have lactic acid, which is HC3H5O3, and I know that's going to dissociate into H positive plus C3H5O3 negative. So can I figure out what my Ka expression should look like?
Totes.
Yes. So it should look like the concentration of H positive times the concentration of C3H5O3 negative divided by the concentration of HC3H5O3. So I need to know the concentrations of all three of these at equilibrium before I can find Ka, correct? Yes?
Yes.
Right. So let's figure out what these concentrations are going to be at equilibrium. Here's my balanced reaction. So my initial concentration. What's the initial concentration I start with? 0.1. You can take those zeros off if you want to so they're not in your way. So my products are going to start at 0. I'm going to lose X for my reactants, gain X for my products. So at equilibrium, I'm going to be at 0.1 minus X, X, and X. Do we all agree with this?
Yes.
Yes, we all agree with this. Okay. So before I can figure out Ka, I've got to figure out what? X. I've got to know X. So I want to know this value of X. Is there any information given to me in this problem that can help me figure out the value of X? The percent dissociated, right? So I know the percent dissociated, 3.7, is equal to. Do I know the amount that dissociated? No, that is what? X. X. Divided by, do I know the initial amount that I started with? Yes, that's what? 0.100, and then I take this whole thing and multiply it by what? 100. Can I solve for X?
Yes, you may now.
Absolutely.
Algebra.
I'm going to cross multiply this and do 3.7 times 0.1, which will give me what? 0.37 is going to be equal to 100 times X, so then I just what? Divide by 100. So then X is equal to 0.0037. Everybody with me so far?
Yes.
So now that I know what X is, here and here, can I figure out my value of Ka? Absolutely, right? All I have to do is plug it into this equation. So Ka is going to be equal to, what's my value of X? 0.0037. So that's my concentration of my hydrogen, and that's also my concentration of what? My negative ion, right? So I can just say that that's equal to 0.0037 squared divided by 1.00 minus what? 0.0037.
Wait, why do you use one?
Why would it be 1?
Oh, sorry, 0.1. I did that
Oh,
earlier.
dang it, you didn't use my ratio.
So when I put this in my calculator, which I don't have because you all have my calculators, there you go. You get 1.4 times 10 to the negative 4.
She's got to know what it's supposed to be. Well, she got the board too, so.
Any questions about exercise 14? We're good? Do you see kind of how to start a problem like this if you're given it and you don't know what to do? Start with what you know. They asked me for Ka, so I know I write my Ka expression. Then figure out, so what do I need to know? I need to know these concentrations. How can I know that? Rice table. They always gave you enough information somewhere to figure it out. You've just got to figure out how to use it. Okay? All right. If there's no questions, we're moving on to exercise 15. Now, so far when we've been finding pH, we've always found pH using a weak acid or a strong acid. Because if I want to know pH, I have to know my concentration of what? Hydrogen. Okay? So now, what if they give me a weak base and ask me for the pH? If they give me a weak base, that means when I find X, X is going to be the hydroxide. So if I take the negative log of hydroxide, is that going to give me pH? No, that's going to give me what? POH. But can I use POH to find pH?
Yes.
Yes. And I should be able to do that easily. All right. So let's look at exercise 15. It says calculate the pH for a 15 molar solution of ammonia, and the Kb for ammonia is 1.8 times 10 to the negative fifth. Okay, now I know the problem up here says weak bases, but you should be able to look and say NH3 is a what? Weak base. You should know that. We've talked about that lots. Okay, so that means anytime I have a weak acid or a weak base, I know I'm going to use a what? Rice table. I'm going to need a rice table. Okay. Now, notice, I'll show you this right quick. When we show acids dissociating, we always take out who?
Water.
Water. I did not include water in this equation, did I? I did not include plus H2O. When you are working with bases, you want to include your water, and I'll show you why. All right. If I was to write the balanced reaction for this not including water, that is what I would get. Can you see what happened without putting the water there? No, you can't. So you want to go ahead and add in your water. Now can I see what happened?
Yes.
Yes, I know ammonia is my base, which means my water has to be acting as my what? Acid. Acids donate, bases accept. So I know I'm going to get NH4 positive and OH negative. Now remember, your water is a what? Liquid. So after I put water in there so I can see what happens in my equation, I'm also going to remember that it's not going to be included in any of my calculations. Okay. So I'm going to start with my rice table. There's my R. Initial. What's my initial concentration of ammonia? 15.0. So my products I'm going to assume are at 0. So when I show my change, I'm going to lose X, gain X, gain X. Now remember, because we're working with acids and bases, it's always just 1X and 2X, but I don't want you to forget your general equilibrium. If this was a 2OH negative, what would I have right here?
2.
A plus 2X, right? Okay. So don't forget to look at your coefficients. Don't get lax on that just because we're working with acids and bases. So at equilibrium, I would be at 15.0 minus X, X, and X. What's my next step?
Next step is find out.
There you go. Plug it into my KB equation. So I know KB is going to be equal to my concentration of my ammonium times the concentration of my hydroxide all over the concentration of my ammonia. Because I had to remember water's not included because water is a liquid. So then I say my KB is 1.8 times 10 to the negative fifth. This is x and x, so I would get x squared. This is 15.0 minus x. What am I going to do with that x on the bottom?
Neglect it.
I'm going to neglect it so I don't have to use the quadratic equation. So now I'm going to cross multiply. 1.8 times 10 to the negative fifth times 15. And I get 2.7 times 10 to the negative fourth. So if I take the square root of both, I get x is equal to 1.6 times 10 to the negative 2 is what I got.
Yeah, but I was.
So now that I have x, that means I know my concentration of what? Of my hydroxide, right? If I know the concentration of my hydroxide, what can I find? What am I going to find before I find pH? My POH, right? So now I know my POH is going to be opposite the log of 1.6 times 10 to the negative 2. So when I put that in my calculator, I get, what's after that, 9? So it needs to round up to a 1.80.
So that's how you find POH?
Same way you find pH, except you're using the concentration of hydroxide instead of hydrogen.
Skinner.
So now can I find my pH?
Yes.
What do I do?
You subtract 14 minus 1.8.
14 minus 1.8, and that will give me
12.2.
12.20.
I did this
No, it's
backwards.
like 15. It's like 15.0. It's just two significant. Because the
No, 15.0 is actually 3 significant figures, but 1.8 is only
okay, yeah, you take the small.
2 significant figures, and you go by the smallest. So since that's 2 significant figures, I know I want my pH in 2 decimal places. Good question. All right, what I want you to do is I want you to look at exercise 16 and I want you to try it by yourself right quick. And I will help you with one thing right quick. It's in your notes, so that's why they expect you to know it. But methylamine is CH3.
Yeah.
It
I
H2.
showed it last time.
That's what?
Alright, you can check your work with my work as you're going to see if you set it up right and you started right. You got what, Zach?
I did 2.09, not 2.09.
That's fine. And if you did something like using like 2.09 there instead of 2.1, it doesn't really matter. It may have changed your numbers a little bit on your POH and your pH, but it doesn't matter. Your sig figs don't matter until you get to the end. Okay? So it doesn't matter what you use for X or anything in here really, as long as you have the correct numbers, significant figures at the end. Right? Is there any questions on 16? Your quiz tomorrow is going to look a lot like either exercise 15 or 16 more than likely. If I'm in a super generous mood, I doubt it. I might make it look like 11. So I would look at 11, 15, and 16.
See you, Phil. Everyone bring food, right?
Still got me one.
So tonight you need to look at exercise 11, 15, and 16. All right, we're going to go over this concept, but we're not going to work another exercise. So just hang with me for a couple more minutes.
Hey.
And we're going to talk about calculating the pH of a polyprotic acid, and then we'll really get into it tomorrow. All right? So, poly means what?
More.
Many. Okay? So, polyprotic acids have more than one hydrogen that they can give away. We've already talked about this before, so this should be kind of a review. Okay? What you need to remember is that they ionize in steps. Okay, so we'll take H3PO4 for example. Okay, phosphoric acid. It has 3 hydrogens that it can give away, but it's not going to give away those 3 hydrogens all at the same time. It's not just going to dump them off 1, 2, 3. It's done. Okay, it's got each dissociation only gets its own Ka values since it happens in steps. Okay, the first dissociation always has the greatest Ka. Okay, so the first dissociation always has the greatest Ka. Why?
Because it's the first. Because it dissociates faster.
Because it's the first one, so it dissociates faster and it dissociates more hydrogens. Okay? After that first hydrogen is removed, so after we remove each hydrogen, the acid starts to get weaker. So when the acid gets weaker, it's not going to give us off as many hydrogens, so then that gives us a smaller Ka. The more negative an acid becomes, so the greater that negative charge becomes, the more difficult it is to remove that hydrogen. Because remember, when we talk about positively charged protons, we're talking about who? H plus, hydrogen. So we'll look at this right quick. So we see H3PO4. When we put it in water, now H3PO4 is my acid, so water is acting as my base. What do acids do with their protons?
Donate.
Donate, and bases accept. So now I get the H3O positive plus the H2PO4 negative. Okay, so look at the value of my first Ka. Now my acid has what charge on it? Negative. So when this same reaction happens again, do I get as many H3O positives this time? No. How do I know I don't get as many H3O positives? Because I can look at my what? Ka value. My Ka value got smaller, so I know I've got less H positives. Now what's happened to my acid? The charge of it's now down to a what?
2 negative.
2 negative. So now it's going to be really hard to lose that hydrogen. So now my Ka has gotten even what?
Smaller.
Smaller.
Excellent.
So you can look at your Kas to get the strength of your acid. And the weaker it gets, you need to realize that means the less hydrogens are going to dissociate. Okay? All right, we'll pick up with exercise 17 tomorrow.